Between the brilliant tapestry of galaxies lies an eerie silence, vast stretches of nothingness, so immense they could swallow our entire Milky Way without a trace. These cosmic voids aren't just empty space, they're silent riddles written in the fabric of reality itself. What if I told you these seemingly barren regions could rewrite the laws of physics? Hidden within their darkness might be answers to dark matter's elusive nature, whispers of undiscovered dimensions, or even echoes of other universes brushing against our own. This isn't just empty space, it's a frontier where our understanding of existence unravels. Stick with me, and by the end of this journey, the universe will feel stranger and more spectacular than you ever imagined. Picture the universe like a colossal sponge, dense clusters of galaxies tangled together, while between them, enormous gaps stretch across the darkness. These are cosmic voids, the universe's ghost towns, where matter is so sparse that if you stood in the middle of one, the night sky would be nearly pitch black. No glittering galaxies, no swirling nebulae, just an unsettling emptiness spanning hundreds of millions of light years. Now, emptiness doesn't mean nothing is happening. These voids are like cosmic wind tunnels, sculpted over billions of years by the push and pull of dark energy and gravity. Think of them as the negative space in a vast celestial painting. What's not there tells us just as much as what is. While galaxy clusters act like knots in a cosmic net, the voids are the gaps where the threads stretch thin. But here's the twist, these voids aren't just passive blanks. They're actively shaping the universe around them. The gravitational pull from surrounding galaxy clusters tugs matter away, leaving behind these ever-expanding deserts. Some scientists believe voids could even be speeding up cosmic expansion, acting like invisible engines driven by dark energy. So why does any of this matter? Because studying voids is like reading the universe's hidden blueprint. They hold clues about how gravity, dark matter, and dark energy interact on the largest scales. If we can decode the secrets of these silent, empty spaces, we might finally understand the forces that built the cosmos itself. The first great mystery lurking in these cosmic voids. A colossal case of missing matter. Scientists call it the missing baryon problem, an enigma as baffling as it sounds. The math says there should be far more ordinary matter floating in these empty expanses than our telescopes can detect. So where did it all go? One leading theory paints a ghostly picture. That missing matter might be hiding as ultra-hot gas, so thinly spread and energetic that it's nearly invisible to our instruments. Think of it like steam. Just because you can't always see it doesn't mean it isn't there. Other researchers speculate these voids could be littered with exotic particles we haven't even discovered yet, remnants from the universe's earliest, most violent moments. But here's where it gets wild. Some astrophysicists believe this matter didn't just vanish, it was kicked out. Powerful forces like ancient supermassive black holes or explosive galactic winds might have blasted it beyond the voids entirely. If true, that would rewrite our understanding of how galaxies and cosmic structures evolve. The stakes couldn't be higher. If our models are wrong, if matter isn't where we think it has to be, then something fundamental in our physics is missing. Solving this mystery could reveal hidden laws of the cosmos or expose gaps in Einstein's theories. Voids aren't just empty spaces, they're cosmic crime scenes, and the case of the missing baryons might be the biggest unsolved mystery in the universe. Now, let's step into one of the most mind-bending aspects of cosmic voids, their bizarre connection to dark energy. These empty expanses aren't just sitting there, they're growing. And not at the universe's average pace, but faster. Like invisible hands stretching the fabric of space-time, these voids are swelling at speeds that defy expectations. And that acceleration, it's a glaring clue that dark energy, the enigmatic force driving the universe's expansion, might be flexing its muscles here more than anywhere else. Think of it this way: if the universe is an inflating balloon, cosmic voids are the spots where the rubber thins out the quickest. While galaxies cluster together, held close by gravity's grip, the voids between them are where dark energy runs wild, pushing space apart with relentless strength. That's why astrophysicists see these desolate regions as the ultimate testing grounds for dark energy's secrets. If we can measure how fast these voids balloon outward, we might finally unravel why our universe is tearing itself apart. But the plot thickens. Some scientists suspect dark energy might not even be a constant force. What if it changes over time? Imagine an invisible hand that sometimes pushes harder and other times eases up. If that's true, the edges of cosmic voids could be where these fluctuations leave their fingerprints. The way voids expand or how their walls of galaxies crumble might hold the key to figuring out whether dark energy is steady. Or something far stranger. Here's the real kicker. If dark energy behaves differently inside voids, it could mean our entire understanding of the cosmos is incomplete. Maybe Einstein's equations need tweaking, or perhaps there's an entirely new physics waiting in these empty deserts. One thing's certain: cosmic voids aren't just blank spaces. They're the universe's most extreme experiments, and the answers they hide could redefine reality itself. But here's something even more surprising: cosmic voids aren't just featureless pits of darkness. Peer closer and you'll find an intricate web of ghostly structures hiding within them. Faint tendrils of galaxies, wispy bridges of gas, and even smaller voids nestled inside the larger ones like bubbles trapped in cosmic amber. Far from being smooth, empty expanses, these regions are riddled with hidden texture, as if the universe left behind subtle brushstrokes in its emptiest places. What's fascinating is how these faint structures might trace back to the very birth of the cosmos. Some researchers believe the delicate filaments inside voids could be fossilized imprints of quantum ripples from the Big Bang, tiny fluctuations stretched into enormous patterns over billions of years. If that's true, these barely their threads would be some of the oldest relics in existence, frozen echoes of the universe's first chaotic moments. Yet there's another possibility that turns this idea on its head. These structures might not just be ancient leftovers, they could be evidence of forces we haven't yet discovered. Maybe dark matter, with its invisible grip, sculpted these faint trails in ways we don't yet understand. Or perhaps another, even more elusive influence, something beyond our current physics, left its mark in these desolate zones. That's why astronomers painstakingly map these nearly invisible features. Like detectives reconstructing a crime scene from dust, they trace the faintest galaxies and wispy filaments, hoping to uncover whether these structures are cosmic fossils or messages from a deeper layer of reality. And the answers won't just tell us about the voids, they'll rewrite the story of how everything in the universe came to be. One thing's certain: the emptiest places in the cosmos are anything but simple. They're riddled with puzzles, each one a clue to forces that shaped existence itself. And if we can decode them, we might finally understand the universe's grand design, one ghostly filament at a time. Deep within these cosmic voids, time itself seems to slow to a crawl. While the rest of the universe buzzes with the collisions of galaxies and the birth of stars, these vast deserts remain eerily unchanged, like snapshots frozen in the aftermath of creation. Scientists suspect they're staring into a time capsule, one that might hold whispers from the universe's first trembling breaths. The sheer scale of these voids is the key. While smaller structures merged and warped over eons, these gargantuan empty regions were too vast to be easily disturbed. That means their shapes and distributions could still carry subtle fingerprints from the Big Bang itself, imprints so delicate they'd be erased almost anywhere else. It's like comparing a weathered mountain to a perfectly preserved snowflake. One shows its age while the other remains pristine. What exactly are researchers searching for? Two cosmic holy grails, primordial gravitational waves and evidence of inflation. These would be ripples in space-time from the universe's violent birth, stretched to enormous scales by its rapid early expansion. Voids act like cosmic amplifiers. Their emptiness lets these faint signals travel undisturbed, like echoes bouncing down an endless hallway. If we can decode them, we might finally witness how space-time itself twisted into existence. But the real magic lies in the geometry. The way voids arrange themselves, their sizes, shapes, and distribution could reveal whether inflation really happened the way we think. Some theories suggest alternate versions of those first explosive moments, where the universe didn't just expand but bubbled into being. If voids cluster in unexpected patterns, they might be cosmic breadcrumbs leading us to a deeper truth. Imagine holding a fossilized bubble from the birth of space itself. That's what these voids could offer, a direct line to the universe's rawest, earliest state. And if we're right, these ghostly expanses won't just tell us where we came from, they might hint at universes beyond our own, forged in the same fiery dawn. The emptiest places in existence could become our richest window into everything. Something peculiar happens when light travels through these cosmic voids. It doesn't just pass through untouched. Instead, it bends, warping ever so slightly like a mirage shimmering in the desert heat. This phenomenon, called gravitational lensing, is more than just a cosmic illusion. It's a detective tool, revealing hidden mass lurking where our telescopes see only darkness. Einstein's theory tells us that any mass, even the sparse matter in these voids, can curve spacetime, deflecting passing light like a hidden lens. Normally, we associate lensing with massive galaxy clusters where the effect is dramatic. But in voids, the distortions are far subtler, like detecting whispers in a silent room. Yet, when astronomers analyze these faint warps, they uncover something startling. There's more mass in these empty regions than expected. So what's casting these gravitational shadows? Some of that hidden mass could be dark matter, drifting in vast, undetectable clouds, or perhaps rogue black holes, lonely behemoths ejected from galaxies, are silently prowling the void, invisible except for the way they tug at passing light. But here's where things get strange. Recent measurements show lensing effects that don't match predictions. The distortions are weaker than they should be, as if something is missing, or worse, as if our understanding of gravity itself breaks down in these desolate stretches. Could voids be exposing cracks in Einstein's theory? Some physicists speculate that an unknown force, maybe a fifth fundamental interaction, could be at play in these emptiness. Others wonder if dark matter behaves differently here, clustering in ways we've never imagined. The truth is, every flicker of lensed light carries a coded message about the universe's deepest secrets. And if we can decipher it, we might not just solve the mystery of the void's shadows, we could rewrite the rules of gravity itself. Amid these vast cosmic deserts, a few stubborn galaxies refuse to be left out, floating in near total isolation like lone travelers crossing an endless wasteland. These are the void galaxies, celestial anomalies that challenge everything we know about how galaxies form and survive. While most galaxies cluster together in bustling cosmic cities, these rare outcasts have thrived, or barely clung to existence in the emptiness, evolving in ways that defy expectations. What makes them so strange? For one, they're cosmic time capsules. Some appear frozen in an ancient state, with fewer heavy elements metals forged in generations of stars than their cluster-dwelling counterparts. That suggests they've been cut off from the usual galactic recycling processes for billions of years, preserving conditions closer to the early universe. Others, bizarrely, are still birthing stars at unexpected rates, as if the void itself is quietly feeding them fuel we can't see. Then there's the shape puzzle. Many void galaxies are oddly symmetrical, pristine spirals untouched by the gravitational tug-of-war that distorts galaxies in denser regions. Without neighbors to pull and warp them, they've grown undisturbed, like trees in a solitary valley growing perfectly straight. But a few are the opposite, misshapen and turbulent, as if the void's emptiness somehow triggered chaotic star formation. The biggest question is why they're there at all. Current theories suggest they might be remnants of early universe filaments that never fully collapsed, or perhaps survivors of a cosmic battle where their neighbors were ripped away by an ancient void's expansion. Whatever their origin, they're rewriting the rules. If galaxies can evolve in total isolation, then our models of how dark matter and gas interact may need a major overhaul. And their rarity is a clue, too. The fact that so few galaxies dare to drift into the void hints at an invisible boundary, a tipping point where the pull of surrounding clusters overpowers the void's emptiness. Studying these galactic hermits could reveal the exact conditions that make the cosmos favor togetherness over solitude. In the end, void galaxies aren't just oddities. They're extreme experiments in survival, showing us what happens when a galaxy is left to fend for itself in the great cosmic wilderness. One of the most perplexing riddles lies in a patch of sky so cold it defies explanation. A mysterious cold spot embedded in the cosmic microwave background, the afterglow of the Big Bang. Stretching nearly 2 billion light-years wide, this eerie chill overlaps with one of the universe's largest known voids, as if the emptiness itself is radiating cold. But here's the catch: the temperature drop is far more extreme than standard physics predicts for a void of that size. It's like opening your freezer to find a blizzard raging inside. Something doesn't add up. For years, scientists debated whether this anomaly was just a statistical fluke, a random quirk in the data. Yet as measurements grew sharper, the cold spot refused to vanish. Now, some researchers propose a jaw-dropping alternative. This supervoid might be the bruise left by a collision with another universe. Imagine two soap bubbles brushing against each other in a cosmic foam. Where they touched, energy could have drained away, leaving behind a chilling imprint in our own reality. The implications are staggering. If true, this void wouldn't just be empty space, it'd be a cosmic peephole into the multiverse. The cold spot's unusual properties align with exotic theories suggesting our universe is one of many, each with its own physics, occasionally nudging against ours. While skeptics argue for less dramatic explanations like an unusually sparse void distorting light in unexpected ways, the possibility of a multiverse signature keeps the debate electrifying. What's undeniable is that this cold, empty patch challenges our understanding of reality's boundaries. Whether it's evidence of a parallel cosmos or just an anomaly we haven't decoded yet, the cold spot forces us to confront a humbling truth. The universe's quietest corners might be shouting the loudest secrets. And if we listen closely, we might hear echoes from beyond the edge of everything we know. In the crushing silence of cosmic voids, where even atoms are scarce, something astonishing might be happening at the smallest scales of reality. At these extremes, the very fabric of space-time could be twisting in ways we've only theorized, where the bizarre laws of quantum physics break free from the microscopic and stretch across the void's vast emptiness. This is the realm of quantum foam, a turbulent sea of virtual particles that flicker in and out of existence, normally hidden from view. But in voids where gravity's grip is weakest and matter's whisper thin, these fleeting fluctuations might leave traces we can actually detect. Imagine empty space not as a smooth, unbroken sheet, but as a bubbling cauldron at the tiniest levels. According to quantum theory, pairs of particles and antiparticles constantly pop into being, only to annihilate each other in an instant, a phenomenon so fleeting it's nearly impossible to observe. Yet in the near-perfect vacuum of a cosmic void, where disturbances are minimal, these quantum ripples might add up to something bigger. Some physicists speculate they could even create faint, measurable distortions, like static on a cosmic radio, humming in the background of nothingness. This isn't just theoretical curiosity. If we could capture this void quantum noise, it might finally bridge Einstein's theory of relativity with quantum mechanics, two pillars of physics that stubbornly refuse to align. Normally, quantum effects vanish at large scales, drowned out by gravity's dominance. But in voids where gravity is diluted to near nothing, quantum behavior might stretch beyond the subatomic, leaving fingerprints on spacetime itself. Here's where it gets wild. One bold hypothesis suggests that if quantum foam is active enough in these voids, it could slightly alter the speed of light passing through, a deviation so tiny it would require unimaginably precise instruments to spot. Others wonder if voids might warp quantum entanglement, the spooky connection between particles across vast distances. Could these empty regions be cosmic laboratories where the rules of physics subtly bend? The stakes couldn't be higher. If we detect quantum signatures in voids, it wouldn't just solve a century-old physics puzzle. It could reveal space-time as something far more dynamic and textured than we ever imagined. We might be on the verge of proving that emptiness isn't passive, but alive with possibility, where the universe's smallest and largest mysteries collide. And the answers won't just hide in equations, they'll lurk in the silent, stretching voids, waiting for us to listen. Strangely enough, even in the deepest cosmic voids, where matter is almost non-existent, faint magnetic fields ripple through the emptiness like phantom currents. These weak but detectable forces shouldn't logically exist in such desolate regions, yet they're there, threading through the void with no clear explanation. Where do they come from, and what invisible hand could be shaping them across billions of light years? One leading theory traces these ghostly fields back to the universe's fiery youth. In the aftermath of the Big Bang, when the cosmos was a turbulent sea of charged particles, powerful plasma currents may have imprinted magnetic lines into the fabric of space itself. Over eons, as the universe expanded and voids formed, those primordial fields stretched and faded but never entirely vanished. Think of them like faded ink on ancient parchment, barely visible yet holding clues to a lost history. But there's a twist. Some researchers argue these fields shouldn't have survived this long without dissipating entirely. That raises a startling possibility. What if something is actively sustaining them? Dark matter, exotic particles, or even undiscovered physics could be at work, generating magnetic energy in places where ordinary matter is nearly absent. It's as if the void itself is whispering to us through these faint forces, hinting at processes we don't yet understand. What's even more intriguing is how these fields might shape the cosmos. Weak as they are, they could act like cosmic scaffolding, guiding gas and dust into the filaments that eventually birth galaxies. Without them, the universe's grand structure might look entirely different. Or perhaps they're not builders at all, but echoes, traces of a hidden electromagnetic web that connects everything, unseen until now. The mystery deepens with every new observation. If we can decode the origin of these void magnetic fields, we might uncover a fundamental force that's been overlooked, one that quietly shapes the universe from the shadows. And that would mean the emptiest places in existence aren't just passive voids but hidden workshops where the cosmos weaves its secrets in silence. Hidden within the walls of cosmic voids, you'll find something extraordinary, an echo of the universe's very first sound. Not a musical note or a whisper, but a thundering shockwave frozen in time, stretching across hundreds of millions of light years. These are Baurian acoustic oscillations, or Bohr cosmic fossils from the Big Bang's violent infancy, when the entire universe was a seething, roiling plasma. Here's how it happened. In the first few 100,000 years after the Big Bang, matter and light were locked in a fierce tug of war. Dense regions of plasma acted like colossal speakers, sending out pressure waves, sound waves, rippling through the newborn cosmos. Then, as the universe cooled, those waves suddenly froze in place, imprinting their rhythm into the distribution of galaxies we see today. Think of it like a fingerprint pressed into wet clay, preserved for eternity. Now, voids play a starring role in this ancient symphony. Unlike galaxy clusters where gravity has scrambled the original pattern, the walls of voids, those thin, filament-like borders between empty regions, still hold these frozen waves in near-pristine condition. By measuring the distance between them, astronomers can reconstruct how fast the universe has expanded over billions of years. It's like using the rings of a tree to read its growth, except here the tree is space-time itself. But there's a puzzle. Some voids show BAOs that don't match predictions. The spacing is off, either stretched too wide or compressed too tight, as if an unseen force has been pulling or pushing on these cosmic echoes. Could dark energy be tweaking the scale, or is there something even stranger at work, an unknown interaction between matter and the void's emptiness, the wildest possibility? These anomalies might be evidence that dark energy isn't constant but evolving. Picture it like an orchestra where the instruments slowly change tuning over time. If BAOs in voids are the sheet music, then the discordant notes could reveal how the universe's expansion has shifted in ways we never predicted. Whatever the answer, one thing's certain: these frozen sound waves are more than just relics. They're the universe's deepest vibrations, humming a tune that began at the dawn of time, and voids are the perfect place to listen. Picture this: an entire civilization growing up in the crushing solitude of a cosmic void, where the night sky holds only a handful of stars, so sparse that constellations would be impossible to form. For any life that might exist in these isolated void galaxies, the universe would appear shockingly empty, their view of the cosmos reduced to a scattering of faint pinpricks against an endless black canvas. How would such isolation shape their understanding of existence? Unlike us, whose ancestors used the stars to navigate, tell time, and craft myths, a void civilization would have no Milky Way arching overhead, no Andromeda looming in the distance. Instead, their celestial landmarks would be ghostly filaments, faint traces of galaxies so far away they'd barely register. Imagine looking up and seeing nothing, no grand tapestry of light, just the void stretching into infinity. Would they even believe in other galaxies before inventing telescopes powerful enough to pierce the darkness? This extreme isolation could rewrite their entire scientific journey. Without nearby stars to study, their astronomy might develop slower, or perhaps faster, driven by sheer desperation to uncover what lies beyond the emptiness. Their version of the Copernican revolution could come far later or far sooner, depending on whether the void's loneliness breeds curiosity or resignation. And if they did turn their instruments outward, what would they make of the strange, crowded universe beyond their bubble? Would it seem like a celestial zoo or a myth too wild to believe? Then there's the question of survival. With so few stars and raw materials, energy would be a constant struggle. A void civilization might master efficiency on a scale we can't fathom, harvesting every scrap of energy from their sparse surroundings. Or perhaps they'd become nomadic, launching vast arcs toward the distant glow of galaxy clusters, chasing the promise of resources we take for granted. But the most haunting thought, they might not even know they're in a void at all. To them, this emptiness could simply be the universe, and the idea of living in a galaxy-rich neighborhood like ours would sound like science fiction. If we ever made contact, their entire world, you might shatter, or worse, they might refuse to believe us, convinced we're just another cosmic myth. The truth is, void life isn't just a question of biology, it's about perspective. Civilizations born in these deserts would see reality in ways we can barely imagine. And if they exist, their story wouldn't just teach us about alien minds, it would force us to question how much of our cosmic understanding is shaped by the accident of where we were born. Einstein's theory holds a startling prediction about these cosmic voids. Time itself doesn't flow evenly here. In regions where gravity's grip is weakest, clocks tick ever so slightly faster compared to the crowded galactic neighborhoods we're used to. It's a subtle effect, but if we could measure it, we'd witness relativity in action on a staggering cosmic scale. And the implications go far beyond mere curiosity. They could reveal whether our understanding of spacetime itself holds up in the universe's emptiest realms. Think of gravity like a weight pressing down on the fabric of time. Near massive objects like stars or black holes, time slows, a phenomenon confirmed by countless experiments. But in voids where matter is almost absent, that weight lifts, letting time speed up. The difference is tiny. A clock here might gain a fraction of a second over billions of years, but for physicists, even that whisper-thin deviation matters. If we detect it, we'd have proof that relativity governs the cosmos even in its most desolate corners. Here's where it gets thrilling. Future missions like NASA's proposed Deep Space Atomic Clock could finally put this to the test. Imagine ultra-precise clocks placed in orbit or on spacecraft drifting through the void, far from any galaxy's gravitational influence. By comparing their ticks to Earth-bound counterparts, we might catch time's faint acceleration in real time, a direct glimpse of Einstein's equations playing out across the cosmic stage. But the real mystery lies in the deviations. What if time in voids doesn't behave exactly as predicted? Some theories suggest dark energy or unknown quantum effects could tweak spacetime's rules in these emptiness. A single anomalous measurement might hint at forces beyond relativity, an unseen hand tweaking the universe's clockwork. That's why voids aren't just empty spaces. They're laboratories for the most extreme tests of physics where time itself becomes the experiment. Picture this, a future where we map the universe not just by light or gravity, but by the flow of time. Voids could become our cosmic speedometers, revealing hidden wrinkles in spacetime's fabric. And if we're lucky, the answers won't just confirm what we know. They'll open doors to realms of physics we've yet to imagine. Deep in the cosmic voids, where ordinary matter barely registers, another mystery lurks. One that challenges our understanding of the universe's hidden architecture. Dark matter, the invisible scaffold that shapes galaxies and galaxy clusters, seems to vanish in these empty regions. Yet according to supercomputer simulations, it should linger here, threading through the void like faint cobwebs. So where is it, and why does its absence or presence rewrite the rules of this enigmatic substance? The puzzle begins with gravity's fingerprints. We know dark matter exists because its gravitational pull tugs on visible matter, bending light and sculpting cosmic structures. But when astronomers map voids, they find something strange. The gravitational distortions are weaker than simulations predict, as if dark matter has gone missing. If these simulations are right, voids should contain vast, diffuse clouds of dark matter, ghostly halos too sparse to collapse into clumps but still detectable. Yet the data suggests these halos might be nearly empty. Some scientists propose a radical answer. Dark matter isn't as smooth as we thought. Instead of spreading evenly, it could form ultra-fine strands or microhalos, clumping on scales too small for our telescopes to resolve. Picture a mountain range seen from space. From afar, it looks like a solid mass, but up close, it's riddled with valleys and gaps. If dark matter behaves similarly, voids might be dotted with invisible pockets we simply can't see yet. Then there's the wilder possibility voids could host an entirely new phase of dark matter. Just as water shifts between ice, liquid, and vapor, dark matter might transform in these extreme environments. Perhaps in the void's weak gravity, it becomes fluffy or even interacts with itself in ways that erase its gravitational signature. If true, that would mean dark matter isn't a single, uniform entity but a substance with hidden complexities adapting to the emptiness around it. The implications are staggering. If dark matter avoids voids, our models of cosmic evolution might need an overhaul. But if it's hiding in plain sight, cloaked by some exotic behavior, then we're on the verge of uncovering its deepest secrets. Either way, these empty expanses aren't just blank spaces. They're testing grounds for the universe's most elusive ingredient, and the answers we find here could finally pull dark matter out of the shadows. At the edges of these cosmic voids, something doesn't add up. The transition from dense galactic walls to empty space is razor-sharp, far more abrupt than our simulations predict. It's as if the universe drew these boundaries with a precise blade, leaving no room for gradual fading. You'd expect galaxies to trail off into the void like sand slipping through fingers. Instead, they stop suddenly, as if hitting an invisible barrier. So what's holding them back? One clue lies in the tug of war between dark energy and gravity. While gravity pulls galaxies together, dark energy pushes space apart, and where these forces clash, voids grow. But at their edges, something amplifies this battle. Some theorists suggest dark energy might concentrate along void walls, acting like a cosmic dam that galaxies can't cross. Picture it like a river hitting a hidden current. The water doesn't just slow, it piles up against an unseen force. Then there's the wilder idea, primordial imprints from the Big Bang itself. Quantum fluctuations in the early universe could have left behind ultra-dense ripples, fossilized seams in space-time that galaxies naturally cluster around. These ancient wrinkles might still linger today, marking where voids begin and end with unnatural precision. It's like finding the faint outline of a mold pressed into clay billions of years later. But the real puzzle, even our best dark matter models struggle to explain why these edges are so defined. If dark matter distributes smoothly, galaxies should bleed into voids gradually. Yet the boundary remains stark, as if an unaccounted force is sculpting it. Could dark matter clump differently near voids, forming invisible scaffolding? Or is there an entirely new physics at play, some undiscovered interaction that locks galaxies into place? Whatever the answer, these sharp edges aren't just cosmic quirks, they're evidence that voids aren't passive absences, but dynamic structures with their own rules. And if we can crack the paradox of their borders, we might uncover forces shaping the universe in ways we've never imagined. The universe doesn't do fuzzy, and that precision could be the key to everything. Here's something almost poetic about cosmic voids. They're so empty, they might be the universe's perfect neutrino traps. These elusive particles, born in the Big Bang's furious first moments, zip through everything: planets, stars, even you, with barely a whisper of interaction. But in the vast, sparse stretches of a void, their faint signals might finally emerge from the cosmic noise like whispers in a silent room. Neutrinos are the ultimate cosmic ghosts. Trillions pass through your body every second, yet they're so light and weakly interacting that detecting them feels like catching smoke with your hands. Most experiments hunt them near dense environments like Earth's core or the Sun, where neutrino production is high. But voids flip the script. Here, the absence of competing signals and the sheer volume of space could make relic neutrinos, those ancient messengers from the universe's infancy, stand out against the quiet backdrop. Why does this matter? Because these aren't just any neutrinos. Relic neutrinos, if we could capture them, would be time capsules from the first second after the Big Bang. They've traveled nearly 14 billion years undisturbed, carrying secrets about how matter triumphed over antimatter, how the fundamental forces split apart, and possibly even clues about dimensions beyond our own. It's like finding a letter sealed at the dawn of time, just waiting to be read. The challenge: their energy is absurdly low, so faint that current technology struggles to spot them. But voids offer a unique advantage. With no stars, galaxies, or magnetic fields to muddy the signal, next-generation detectors placed in or aimed at these empty regions might finally have a shot. Some proposals even suggest using the void's natural emptiness as a filter, letting everything except these primordial neutrinos fade into the background. And here's the tantalizing twist: if relic neutrinos behave unexpectedly in voids, say, clustering in ways they shouldn't or revealing energy discrepancies, it could hint at physics beyond the standard model. Maybe they interact with dark matter in ways we've never imagined, or perhaps they're subtly warped by hidden dimensions curled up in the fabric of space. Voids might seem like the last place to hunt for particles, but that's exactly why they're ideal. In the universe's quietest corners, the faintest echoes linger longest. And if we're right, these ghostly neutrinos could turn cosmic voids into the ultimate time machines, letting us peer back further than telescopes ever could, to the very edge of existence itself. Amid the overwhelming silence of cosmic voids, there's a whisper, faint but unmistakable. It's the scent of hydrogen, the universe's most basic ingredient, drifting through the emptiness in sparse, ghostly clouds. Unlike the dense molecular clouds where stars are born, this hydrogen is so diffuse it would register as a near-perfect vacuum on Earth. Yet against the backdrop of absolute nothingness, these wispy atoms emit something extraordinary, a faint but detectable radio hum, a relic signal echoing from the dawn of time. This isn't just background noise, it's a cosmic breadcrumb trail. When the first stars ignited, their fierce ultraviolet light ripped electrons from hydrogen atoms, ionizing them in an event called reionization. The traces of neutral hydrogen left behind in voids are like fossilized smoke from that ancient fire, preserving a record of how the universe transitioned from darkness to light. Now, next-generation telescopes like the Square Kilometre Array, or SCAR, are tuning into these whispers, aiming to map this signal with unprecedented precision. But the real magic lies in the anomalies. If the hydrogen in voids is distributed exactly as predicted, it'll confirm our models of cosmic evolution. If not, that's when things get thrilling. Unexplained gaps or unexpected clustering could hint at forces beyond our current physics, perhaps dark matter interacting in subtle ways, or primordial magnetic fields sculpting the gas from behind the scenes. Even stranger, some theorists speculate these hydrogen clouds might carry imprints of quantum fluctuations from the Big Bang itself, stretched to cosmic scales by the void's expansion. What's at stake goes beyond hydrogen. Mapping these faint radio waves could expose how voids acted as cosmic mixing bowls, channeling and diluting the raw elements forged in stars. Over billions of years, this process shaped the chemical diversity we see today, the very ingredients that made planets and life possible. If we decode these whispers, we're not just studying emptiness, we're uncovering the recipe for everything. And the most tantalizing possibility: if the signal deviates from expectations, it might not just rewrite astrophysics, it could reveal voids as portals to something deeper, where the universe's oldest secrets are still humming, barely audible, waiting for us to listen. 17th mystery: void black holes, the invisible rogues of empty space among the countless galaxies, stars, and planets in the cosmos. There's a stranger lurking in the dark, black holes that don't belong to any galaxy at all. These are the rogue black holes, drifting through cosmic voids like unseen predators, cloaked in perfect darkness. Without stars to light their way or accretion disks to betray their presence, they remain nearly undetectable until they bend the very fabric of space itself. How do these solitary giants end up in the void? Some might have been flung out of their home galaxies during violent collisions, ejected by gravitational slingshots. Others could be relics of the universe's earliest days, primordial black holes, born not from dying stars but from the extreme density fluctuations of the infant cosmos. If they exist, they'd be cosmic fossils untouched by time, wandering the emptiness since before the first galaxies formed. The real challenge is finding them. Unlike their active counterparts, rogue black holes don't feast on gas or rip apart stars. They're silent, invisible, and all but undetectable. But there's one telltale sign: gravitational lensing. When a rogue black hole drifts between us and a distant background star or galaxy, its immense gravity can warp the light passing by, briefly magnifying or distorting it like a cosmic magnifying glass. These fleeting distortions, called microlensing events, might be our only way to spot them, and that's where the mystery deepens. Astronomers have detected unexplained lensing effects in voids, tiny flashes or warps that don't match any known object. Could these be rogue black holes, far more numerous than we ever imagined? Some theories suggest they might even account for a fraction of dark matter, hiding in plain sight all this time. If so, the voids aren't as empty as they seem. They're teeming with invisible giants, their gravity shaping the universe from the shadows. But there's another, even wilder possibility. What if some of these black holes predate the Big Bang? Hypothetical relic black holes formed in a previous cosmic cycle could have survived the birth of our universe, making them older than time itself. If voids harbor such ancient wanderers, they wouldn't just rewrite black hole physics, they'd force us to rethink the very origins of reality. Whether ejected from galaxies, born in the Big Bang's chaos, or left over from a universe before ours, void black holes are more than just cosmic oddities. They're silent witnesses to the universe's most violent and mysterious chapters, and if we can learn to see their unseen influence, they might finally reveal secrets no telescope could ever glimpse on its own. Amid the crushing silence of cosmic voids, something unexpected cuts through the darkness. Cosmic rays, nature's most energetic particles arriving with no traceable origin. These aren't your average cosmic rays, they're ultra-high-energy bullets packing enough punch to rival a professional fastball. Yet they seem to emerge from the universe's emptiest neighborhoods. That's like hearing a thunderclap erupt from the center of a desert. No storm in sight, just raw, unexplained power. So what's hurling these particles across the cosmos, and why do voids seem to be their launchpad? The first clue lies in their energy. Typical cosmic rays come from violent sources like supernova or active galaxies, but the ones linked to voids defy explanation. They're so energetic, in fact, that our models struggle to explain how any known object, even a supermassive black hole, could accelerate particles to such extremes without breaking physics as we know it. Some researchers speculate voids might harbor hidden particle accelerators, perhaps powered by rogue magnetic fields twisting through the emptiness. Others wonder if the voids themselves act as cosmic magnifiers, stretching and amplifying weaker signals into something far more potent. Then there's the exotic possibility. Voids could be hiding failed stars we've never seen. Imagine quark stars, hypothetical remnants so dense they're made entirely of subatomic particles crushed into a bizarre, ultra-stable state. If these lurk in the darkness, their unimaginable gravity could slingshot particles to near light speeds, creating the very rays we detect. Even stranger, some theories suggest primordial black holes, tiny, ancient relics from the Big Bang, might be lurking in voids, their evaporating edges spraying out energy in bursts we'd register as cosmic rays. Yet the real enigma is the lack of a smoking gun. When astronomers trace these rays back to their supposed origins, they find nothing. No galaxies, no quasars, not even a wisp of gas to hint at what's behind them. It's as if the voids are taunting us, offering cosmic rays like cryptic postcards with no return address. Could this mean our maps of the universe are missing entire categories of objects? things too dark, too diffuse, or too alien to spot with current tools. One thing's certain, if voids are indeed cosmic ray factories, they're rewriting the rules of particle physics in real time. Every unexplained burst from the emptiness is a challenge to our understanding of how energy moves through the universe. And if we ever pinpoint their source, it won't just solve a mystery, it might unveil a new chapter in astrophysics, written in the void's invisible ink. There's a cosmic dance unfolding in the darkness, one we've only just begun to witness. Cosmic voids aren't static wastelands, they're evolving entities growing, shifting, and possibly even colliding over billions of years. But how and what happens when these vast emptinesses interact? The answers could rewrite our playbook on how the universe structures itself and why it's stretching apart faster than we ever predicted. Picture a void not as a fixed bubble, but as a living thing expanding as dark energy pushes the universe outward, its walls thinning like stretched fabric. Galaxies at the edges are caught in a tug of war. Gravity tries to pull them together while the void's growth yanks them apart. Over time, some voids balloon so large they swallow smaller neighbors, merging into titanic voids that dwarf entire superclusters. Others might fragment, their walls collapsing inward like deflating balloons. The problem: our simulations can't agree on which fate dominates. Some show voids growing endlessly. Others suggest they reach a limit before dissolving back into the cosmic web. This isn't just academic curiosity. If voids grow faster than expected, it could mean dark energy is stronger in these regions, or that our models of gravity falter at the largest scales. Even stranger, if voids merge, their combined emptiness might create supervoids, so vast they warp the cosmic microwave background, leaving cold spots like cosmic fingerprints. But the real shocker: voids might not even follow a single rule. Some could expand while others collapse depending on their surroundings. Imagine a universe where emptiness has its own life cycle, some voids born from the chaos of galactic collisions, others dying as matter trickles back in. It's a reminder that even the nothingness out there is teeming with drama, and the way these voids live and die could reveal the universe's ultimate fate. One thing's certain: the emptiest places in existence are anything but quiet. They're the stages where dark energy, gravity, and time itself play out their most epic battles. 20th mystery: the void's infrared glow, invisible light from the emptiness even in the deepest cosmic voids where starlight barely reaches and matter is almost non-existent. A faint, ghostly glow lingers in the infrared spectrum. It shouldn't be there. These regions should be pitch black, devoid of the cosmic engines that light up the rest of the universe. Yet something is radiating heat, whispering in wavelengths we can't see with our eyes, but that telescopes like the James Webb Space Telescope (JWST) are now uncovering. So what's casting this eerie glow? The leading suspects are hidden dwarf galaxies, tiny, dim star systems so faint they've slipped past our detection until now. Like fireflies in a vast, dark field, these overlooked galaxies could be swarming in the void, their combined starlight just enough to create a diffuse infrared haze. If that's the case, it would mean voids aren't quite as empty as we believed. They're simply filled with objects too faint for our telescopes to spot individually. But there's another possibility: warm dust. Unlike the frigid expanse of deep space, even slightly warmer particles emit infrared radiation. Could ancient supernovae, long since faded from view, have scattered dust grains across these voids where they now float, gently radiating leftover heat? Or perhaps interstellar filaments, stretched thin over billions of years, still cling to traces of warmth, glowing faintly like dying embers. Then comes the most tantalizing explanation: decaying dark matter. If this mysterious substance isn't completely stable, some theories suggest it could slowly break down, releasing energy as it does. The infrared glow might be the signature of dark matter particles annihilating one another in the void's near-perfect vacuum. It's a long shot, but if true, it would be the first direct clue to dark matter's true nature. JWST is now scanning these voids with unprecedented precision, hunting for the source of this ghostly light. Whether it's hidden galaxies, drifting dust, or something far more exotic, the answer won't just solve a cosmic mystery, it could redefine what we consider empty space. One thing's clear, even in the darkest corners of the universe, there's more than meets the eye, and sometimes the faintest glow carries the brightest revelations. 21st Mystery. The void's multiverse scars imagine our universe as a single soap bubble floating in an endless cosmic froth, a multiverse teeming with other bubble universes, each with its own physics, its own laws. Now picture those bubbles occasionally brushing against each other, leaving faint imprints where they touch. Cosmic voids might be the very spots where these collisions left their mark, ghostly bruises etched into the fabric of our reality. The evidence could lie in subtle irregularities, patches where the cosmic microwave background, the afterglow of the Big Bang, is slightly cooler or denser than it should be. These anomalies aren't random noise, they're mismatches that defy standard cosmology. Some researchers argue they could be the cosmic equivalent of fingerprints pressed into soft clay, evidence of another universe nudging against ours long ago. But how, if another universe grazed ours during its earliest, most malleable moments, the energy transfer could have created ripples in space-time, frozen into voids as they expanded? Think of it like a slow-motion car crash where the dent lingers long after the impact. These scars wouldn't just be curiosities, they'd be the first tangible hints that we're not alone in the multiverse. Not everyone's convinced, of course. Skeptics point out that cosmic variance, natural randomness in the universe's structure, could explain the oddities without invoking other universes. But here's where voids offer a unique test. If these anomalies cluster along the edges of voids, where space-time is least disturbed by galaxies and matter, the case for a multiverse collision grows stronger. It's like finding a perfectly preserved footprint in an otherwise untouched desert. The stakes couldn't be higher. If voids really are cosmic bulletin boards carrying messages from other universes, decoding them would revolutionize not just cosmology, but philosophy itself. Are we one of countless bubbles in a grand cosmic foam? Or are these voids just playing tricks on us, revealing the limits of our current physics? Either way, the emptiest places in existence might be hiding the most crowded truth of all, that our universe is just one note in an infinite symphony. 22nd Mystery. The void's hidden role in lighting up the universe. Imagine the early universe as a dark, foggy room, filled with thick hydrogen gas that smothered all light. Then, suddenly, the first stars and galaxies flickered to life, their intense ultraviolet radiation burning away the cosmic fog in a process called reionization. But here's the twist: this didn't happen evenly. Some regions cleared first, while others lingered in darkness for millions of years. The key to this patchwork. Cosmic voids, their vast, empty corridors may have acted like highways for UV light, shaping where and when the universe became transparent. Most theories assume reionization was driven solely by galaxies, their radiation ionizing nearby hydrogen like candles melting frost. But voids add a fascinating layer. Their sheer emptiness meant UV photons could travel farther without being absorbed, allowing light to punch through the cosmic haze at incredible distances. Think of it like sunlight streaming through a forest where dense trees block the rays, but open clearings let beams stretch uninterrupted. Voids may have been those clearings, channeling radiation across the cosmos faster than anyone predicted. This could solve a long-standing puzzle: why certain regions of the universe reionized earlier than others. If voids funneled light efficiently, Their geometry might explain why some bubbles of ionized hydrogen grew rapidly while others lagged. Simulations now suggest that the largest voids acted as cosmic amplifiers, their walls reflecting and redirecting UV radiation in ways that supercharge the process. It's as if the universe's emptiest places weren't just bystanders, they were collaborators, shaping the very conditions that made the cosmos visible, yet mysteries remain. Some observations show ionized patches that don't align neatly with void structures, hinting at forces we haven't accounted for. Could magnetic fields or dark matter have altered the path of radiation? Or perhaps early black holes contributed bursts of energy that voids then distributed? The answers might lie in the faintest signals, whispers of hydrogen from the reionization era, detectable only by next-generation telescopes like the James Webb. One thing's certain, if voids played matchmaker between the first starlight and the cosmic fog, they weren't just empty space. They were the universe's first fiber optic cables guiding the dawn of light itself. And that means understanding them isn't just about the voids, it's about how we all came to see the cosmos at all. 23rd mystery, voids quantum entanglement, the universe's spooky long-distance call. Here's something utterly bizarre. Two particles separated by billions of light years, instantly influencing each other's behavior. No signal, no delay, as if space itself doesn't exist between them. This is quantum entanglement, one of physics' most bewildering phenomena, and cosmic voids with their near-perfect emptiness might be the ultimate testing ground to see if this spooky action at a distance holds up across the universe's most extreme scales. Normally, entanglement is fragile, like a whispered secret lost in a crowded room. Even a single stray photon can break the connection. But in the void's pristine quiet, where matter and interference are almost non-existent, entangled particles could theoretically stay linked across staggering distances. If we could measure this, it would push quantum theory into uncharted territory. Does entanglement weaken over cosmic scales, or does it defy our expectations, binding particles no matter how far apart they drift? The challenge: we can't just set up an experiment inside a void. Instead, astronomers look for natural proxies like pairs of distant quasars whose light polarizations might hint at entanglement preserved since the early universe. If their photons match in ways classical physics can't explain, it could mean quantum connections survived the void's expanse. Other proposals involve cosmic inflation. If entanglement stretched along with spacetime during the Big Bang, voids might preserve these stretched quantum threads like faint cosmic cobwebs. But here's the twist: if entanglement does break down in voids, it might reveal something even more startling, that gravity, dark energy, or some unknown force disrupts quantum links at vast scales. That would mean our current physics is missing a crucial piece, one that only emerges in the universe's emptiest realms. Picture the implications. If entanglement holds, voids could become quantum communication highways not for us, but for the universe itself, encoding information in ways we're only beginning to grasp. If it fails, we're staring at a boundary where quantum rules bend or shatter. Either way, these silent deserts aren't just empty. They're the universe's most extreme physics labs, running experiments no human could ever replicate. And the answers won't just rewrite textbooks, they'll redefine reality's deepest rules. 24th mystery: the void's vanishing supernova. The universe loves a good explosion. Supernova blast through the cosmos with enough energy to outshine entire galaxies, scattering the elements that build planets and life itself. But there's a strange silence in the voids. These vast cosmic deserts, already sparse in stars, seem to have an even more peculiar quirk: far fewer supernovae than astrophysicists predict. Where are all the dying stars, and why does the void seem to cheat death in ways we don't understand? Star death isn't random. In galaxy-rich neighborhoods, supernova erupt like clockwork. Massive stars burn bright and fast, collapsing in violent detonations. But voids play by different rules. With so few stars to begin with, you'd expect fewer explosions. Sure, yet even accounting for that, the numbers don't add up. Advanced sky surveys have turned up a glaring mismatch. Voids host only a fraction of the supernova simulations say they should. It's as if the stars here are refusing to die the way they're supposed to. One possibility is downright eerie void stars might age differently. In the emptiness where gas and dust are nearly absent, stars could form with fewer heavy elements, altering how they burn and collapse. Imagine a candle in a windless room versus one battered by gusts. The environment shapes its lifespan. If void stars burn slower and cooler, they might avoid the cataclysmic explosions we're used to, fading quietly instead of going out with a bang. But there's a more unsettling alternative. What if the supernova are happening just too faint for us to see? Standard models assume most dying stars in voids are massive, destined for dramatic explosions. Yet if void galaxies harbor an unseen population of smaller, dimmer stars, their deaths might produce weak, fleeting supernova that slip past our telescopes. It'd be like missing fireflies in a pitch-black field. We're only spotting the brightest sparks. The implications ripple far beyond voids. If star death behaves differently in these emptinesses, it could mean our understanding of stellar evolution is incomplete, or that the universe has more than one way to end a star's life. Worse, if we're underestimating faint supernova, we might be missing a hidden chapter in the story of how elements spread through the cosmos. Iron in your blood, calcium in your bones, these were forged in dying stars. If voids hide their own kind of explosions, they could be quietly seeding the universe with elements we've yet to account for. Perhaps the greatest irony. The emptiest places in the cosmos might be hiding explosions we never knew existed. And solving this mystery won't just rewrite the rules of stellar death. It could reveal an entire shadow population of supernova flickering unseen in the dark. 25th mystery. The void's hidden threads, cosmic strings lurking in the emptiness. The universe might be stitched together by invisible flaws, ancient scars in the fabric of spacetime itself. These hypothetical fractures, called cosmic strings, are thought to be leftover defects from the Big Bang, thinner than an atom yet denser than a neutron star. And if they exist, cosmic voids could be where they hide, stretched like phantom wires across the universe's emptiest expanses. Picture spacetime as a frozen lake. When water turns to ice, tiny cracks form from the sudden tension. Similarly, as the newborn universe cooled and expanded, cracks might have formed in the structure of reality, one-dimensional flaws with unimaginable gravitational pull. Unlike black holes which warp space into a pit, cosmic strings would slice through it like a razor, creating bizarre distortions. Light passing near one would bend sharply, and if a string vibrated, it might even emit faint gravitational waves detectable across the cosmos. Why look for them in voids? It's all about noise. In galaxy clusters, the chaos of stars, gas, and dark matter drowns out subtle signals. But in the pristine quiet of a void, even the faintest twitch of a cosmic string could stand out. Astronomers hunt for their fingerprints in strange, duplicate images of distant galaxies, a sign that a string's gravity has split the light like a prism. They also scan for unexplained bursts of radio waves or gamma rays, which might betray a string's violent oscillations. The wildest possibility, these strings could be time machines. According to some theories, a loop of cosmic string moving at near light speed might twist spacetime so severely that it creates closed time-like curves, paths that loop back on themselves. While that's firmly in the realm of speculation, it underscores how mind-bending these objects could be. They're not just cosmic relics, they're potential keys to understanding whether the universe itself has a grain, a hidden structure woven into its emptiness. For now, cosmic strings remain theoretical, but voids offer the cleanest laboratory to test their existence. If we ever find one, it won't just confirm a decades-old prediction. It'll reveal that the universe's emptiest places are threaded with scars from its birth, silent witnesses to the moment everything began. 26th Mystery: the void's dark flow, a cosmic river pulled by the unknown. Something unsettling is happening on the grandest scales of the cosmos. Galaxies and entire clusters aren't just drifting apart as the universe expands. Some are streaming in the same direction, like leaves caught in a hidden current. Astronomers call this eerie motion the dark flow, and it defies everything we know about cosmic mechanics. These galaxies are being pulled toward a single, mysterious point, one that might lie outside our observable universe. And the strangest part, cosmic voids could be the channels guiding this inexplicable exodus. At first glance, dark flow shouldn't exist. After the Big Bang, matter scattered in all directions, and today's expansion stretches space uniformly, or so we thought. Yet detailed maps show hundreds of clusters all drifting toward the same patch of sky, as if tugged by an unseen hand. The force behind this would need to be unimaginably vast, far beyond the gravitational pull of any known structure in our universe. That's led some theorists to a radical idea: the source might not be in our universe at all. Here's where voids enter the picture. These vast, sparsely populated regions could act like cosmic funnels, their emptiness offering minimal resistance to whatever's pulling. Think of them as cosmic highways where gravity's grip is weakest. Even subtle forces might steer matter more easily. If dark flow follows the paths carved by voids, it could mean these empty regions are more than just absences. They're the universe's connective tissue, pointing toward influences beyond our current physics. One spine-tingling possibility: higher dimensions. String theory suggests our universe might be a membrane floating in a higher dimensional space, with other universes hovering nearby. If one of those unseen realms exerts gravity, leaking into ours, it could create a directional tug like a magnet pulling iron filings through a sheet of paper. Voids, with their sparse matter, might amplify this effect, letting the phantom gravity of another universe guide our galaxies like unseen marionette strings. Of course, not everyone's convinced. Skeptics argue these motions could stem from flaws in our measurements or overlooked local forces. But with each new observation, the mystery deepens. If dark flow is real, and if voids truly are its conduits, we're not just mapping the cosmos. We might be glimpsing the architecture of reality itself. And that means the emptiest places in existence could hold the key to universes beyond our own. 27th Mystery: the void's primordial black holes, ancient shadows from the dawn of time tucked away in the hollowness of cosmic voids. Some of the universe's oldest relics might be hiding, not stars, not galaxies, but tiny, ancient black holes forged in the Big Bang's first chaotic moments. These aren't the monstrous supermassive beasts we're used to. These are microscopic, some no heavier than an asteroid, yet they could hold the answer to one of cosmology's biggest questions: what is dark matter? The theory goes like this. In the searing heat of the early universe, quantum fluctuations may have compressed matter so tightly that pockets collapsed directly into black holes, some as small as a pinprick, others as massive as planets. Unlike stellar black holes born from dying stars, these primordial ones would have formed when spacetime itself was still settling into shape, and if they exist, their perfect hiding spot. The cosmic void, with no galaxies to distract, no stars to outshine them, these elusive objects could drift unseen until they don't. Because here's the twist: tiny black holes don't last forever. According to Hawking radiation, they should slowly evaporate, their energy leaking away as faint bursts of gamma rays. If voids are dotted with these dying pinpricks of gravity, their final moments could create a faint, omnivorous cosmic glow, a whisper of high-energy light just waiting to be spotted. Telescopes like the Fermi Gamma Ray Space Telescope have already caught puzzling excesses of gamma radiation in otherwise empty space. Could this be the smoking gun of primordial black holes fading into the dark? But the implications go deeper. If enough of these primordial black holes populate the voids, they might collectively account for dark matter. Unlike exotic particles, which remain purely hypothetical, these ancient gravity wells would interact with the universe in a way we already understand through their sheer mass. They wouldn't clump like traditional matter but spread diffusely, matching the shadowy gravitational effects we attribute to dark matter. It's an elegant solution. Dark matter might not be a particle at all, but a swarm of cosmic fossils from the universe's first second. Of course, not everyone's convinced. Critics argue that if primordial black holes were this common, we'd see more evidence, like distorted starlight from their microlensing effects. Yet voids offer a loophole. In these near-empty regions with so few stars to lens, these black holes could easily slip under the radar. Their gamma-ray whispers might be the only trace they leave behind. The search is on. New gamma-ray observatories, combined with gravitational wave detectors, could finally catch these evasive objects in the act, either confirming their role in dark matter or forcing us back to the drawing board. Either way, the idea that the universe's emptiest corners might be teeming with black holes from the dawn of time is too tantalizing to ignore, and if we're right, the voids aren't just empty. They're graveyards for the universe's first dark titans, quietly unraveling as they reveal their secrets. 28th Mystery, the void's silent symphony, gravitational waves from nowhere deep in the cosmic voids, where galaxies are few and far between. Something extraordinary might be happening in absolute silence. Supermassive black holes, lurking in isolated void galaxies, could be spiraling toward cataclysmic collisions. Unlike the crowded galactic cores we're used to, these mergers would unfold in near-total isolation, sending ripples through space-time so clean and undisturbed that they'd ring like perfect cosmic bells. And if we can tune in, these void chirps might rewrite what we know about black holes, gravity, and the universe's loneliest corners. Think of gravitational waves as the universe's soundtrack, a faint hum of vibrations from massive objects warping the fabric of space-time. Most of the waves we've detected so far come from dense regions, like colliding neutron stars or black holes in bustling galactic hubs, but voids, they offer something unique. Without the chaos of surrounding gas, stars, or other black holes, waves from a void merger would travel billions of light years almost untouched, carrying a purer signal than anything we've heard before. It's like comparing a symphony recorded in an echo-filled concert hall to one played in the silence of deep space, every note crisp, every detail preserved. Why does this matter? Because these waves could reveal black holes unlike any we've seen. Isolated void galaxies might host black holes that grew differently, slower, quieter, or through exotic means, leaving distinct fingerprints in their gravitational waves. Some theories even suggest void black holes could be primordial, forged in the Big Bang's chaos rather than from dying stars. If their waves deviate from predictions, it might hint at entirely new physics hiding in the emptiness. The challenge is catching them. Current detectors like LIGO and Virgo are tuned for nearby, loud collisions, but future observatories like the space-based LISA mission could be sensitive enough to pick up these distant, pristine signals. Imagine a gravitational wave observatory so precise it hears the universe's faintest whispers, decoding mergers that happened before Earth even formed. But here's the real twist. If void mergers are more common than expected, it could mean black holes thrive in isolation in ways we never predicted. Or worse, that our cosmic census of black holes is missing an entire population lurking in the dark. Either way, these silent, invisible collisions aren't just cosmic oddities. They're golden opportunities to listen to the universe's clearest, most untarnished messages broadcast from the emptiest places imaginable. So while voids may seem like the universe's quietest corners, they could soon become its most revealing. And when those first void chirps finally reach us, they won't just tell a story of colliding giants, they'll sing an entirely new chapter in the saga of spacetime itself. 29th Mystery, the void's exotic matter, a hidden quantum playground. There's a bizarre possibility lurking in the universe's emptiest stretches. What if cosmic voids aren't just empty, but filled with matter unlike anything we've ever seen? Not the familiar atoms and particles of our everyday world, but something far stranger, exotic states that defy the rules of conventional physics. In the near-perfect vacuum of these voids, where density is almost zero and temperatures plunge, the conditions might just be extreme enough to sustain matter in forms too fragile to exist anywhere else. Take strange matter, for example, a hypothetical substance made of strange quarks, a heavier, more unstable cousin of the particles that build protons and neutrons. Under normal conditions, this stuff would instantly decay. But in the void's isolation, shielded from collisions and disruptions, could strange matter survive in fragile, wispy clouds? Some theories suggest that if even a speck of it formed during the Big Bang, it might still drift undetected through these desolate regions, too sparse for our instruments to catch. Then there's quark-gluon plasma, a primordial soup that existed trillionths of a second after the Big Bang, where quarks and gluons roamed freely instead of being locked inside atoms. While we've recreated this state in particle colliders, it vanishes instantly. But in voids where gravity's pull is feeble and interactions are rare, could remnants of this plasma linger, stretched into gossamer-thin veils? If so, spotting it would be like finding a droplet of the early universe frozen in time. But the real enigma, these exotic states might be invisible to our current tools. Without enough density to emit light or distort spacetime noticeably, they could hide in plain sight. The only hints might come from ultra-sensitive quantum sensors or anomalies in cosmic ray data, tiny deviations that whisper something's out there. Of course, skeptics argue that voids are just empty. Yet history has taught us that the universe loves surprises. If even a fraction of these voids harbor exotic matter, it wouldn't just be a curiosity, it'd rewrite the rules of particle physics, revealing phases of reality we've never dreamed of. And that's the thrill of the void. The quieter the space, the louder the secrets it might be keeping. 30th Mystery. Voids, time capsules, pristine gas from the cosmic dawn, tucked away in the deepest voids, far from the cluttered neighborhoods of galaxy clusters. A handful of isolated galaxies drift like solitary survivors. These cosmic hermits might hold something extraordinary, gas so untouched, it's practically a fossil from the universe's infancy. While most galaxies have spent billions of years churning and recycling their material through generations of stars, void galaxies could be frozen in time, their raw ingredients preserved like a sealed vault from the cosmic dawn. Unlike the gas in our Milky Way polluted with heavy elements forged in countless supernova, void galaxies might still harbor pockets of primordial hydrogen and helium, pristine relics from before the first stars ever flickered to life. Imagine finding a vial of untouched seawater from an ancient ocean, untainted by modern pollution. That's what these void galaxies could offer, a direct sample of the universe's original recipe. But how did this gas survive unscathed? The answer lies in the void's extreme isolation. With no neighboring galaxies to collide with, no torrents of cosmic wind stripping away their gas, these lone galaxies have remained sheltered from the usual cosmic turbulence. They're like untouched islands in a vast ocean, preserving conditions that vanished everywhere else eons ago. Now, astronomers are racing to study these cosmic time capsules. By analyzing their light with ultra-sensitive telescopes like the James Webb, scientists can decode the chemical signatures of their gas. If it truly lacks heavy elements, it would confirm these galaxies are living snapshots of the universe's earliest epochs. Even more exciting if their gas shows unexpected quirks like unusual ratios of hydrogen isotopes. It might hint at processes we've never accounted for in our models of cosmic evolution. Of course, not every void galaxy is a perfect relic. Some might have been contaminated over time by stray supernova or faint mergers too subtle to detect. But the mere possibility of finding even one pristine specimen is enough to rewrite textbooks. These galaxies aren't just oddities, they're portals to a time before stars, before planets, before anything but the raw ingredients of existence. And if we can unlock their secrets, we won't just learn about the past. We'll finally understand what the universe was made of before anything else came along to change it. So the next time you gaze up at the night sky, remember, the emptiest places out there might be hiding the purest remnants of all. And somewhere in that darkness, a galaxy could be holding the answers we've been searching for since astronomy began. 31st Mystery. Void's cosmic web nodes the universe's hidden blueprint at first glance. Cosmic voids seem like blank spots in the universe's random gaps between galaxies. But look closer and a breathtaking pattern emerges. These empty regions aren't just accidents. They're critical junctions in the cosmic web, the grand filamentary structure that binds everything together. Like the gaps in a spider's silk, their shapes and sizes aren't arbitrary, they're precise signatures, encoding secrets about dark matter's invisible scaffolding and dark energy's relentless push. To understand why, picture the universe as a colossal 3D puzzle. Galaxy clusters form the dense knots connected by wispy filaments of gas and dark matter. The voids, they're the hollows where those threads stretch thin, but their geometry isn't random. Simulations show that the way voids tilt, merge, or fragment over time depends entirely on how dark matter and dark energy sculpt the cosmic web. A spherical void might hint at calm expansion, while a stretched, irregular shape could betray violent gravitational tugs from unseen structures. It's like reading tea leaves, except the leaves are gaps in spacetime. Here's what makes this so powerful. Voids are sensitive in ways crowded galaxy clusters aren't. In dense regions, gravity's chaos scrambles primordial signals, but voids, with their sparse matter, preserve cleaner imprints of cosmic history. By mapping their distributions, astronomers can essentially reverse engineer the universe's growth. For instance, if voids cluster more tightly than expected, it might mean dark energy is stronger at large scales. If their walls are thicker, dark matter's grip could be firmer than models predict. The real breakthrough came when scientists noticed voids align in eerie, large-scale patterns, almost as if they're nodes on a hidden grid. Some theories suggest these alignments trace back to quantum ripples from the Big Bang, frozen into the cosmic web as it expanded. Others propose they're shaped by dark flow, the mysterious current pulling galaxies toward the unknown. Either way, voids aren't just empty space, they're decoders, translating the universe's underlying architecture into a language we're just learning to read. So next time you hear cosmic void, don't think of absence, think of a cosmic X-ray. These hollows illuminate the invisible forces shaping everything from the smallest galaxy to the fate of the cosmos itself. And with cutting-edge telescopes now charting millions of voids in unprecedented detail, we're on the verge of cracking their code, one empty space at a time. 32nd Mystery. The void's holographic code. Is our universe a cosmic illusion? What if everything we see, galaxies, stars, even the vast cosmic voids, is nothing more than a projection, like a movie playing on the surface of an unseen screen? This isn't science fiction, it's the holographic principle, one of physics' most mind-bending theories. and these expansive, near-empty voids might be the perfect testing ground to uncover whether our universe is really a three-dimensional illusion encoded on a hidden two-dimensional surface. The idea stems from black hole physics, where scientists discovered something astonishing. The information swallowed by a black hole isn't truly lost. Instead, it's somehow preserved on the event horizon, the boundary where light can no longer escape. This led to a radical thought. If a black hole's interior can be stored on its 2D surface, could the entire universe work the same way? That's the holographic principle in a nutshell. The suggestion that all the depth, motion, and complexity we experience might just be data painted on a cosmic canvas we can't yet perceive. Now here's where voids become crucial. Most of the universe is a chaotic mess, galaxies colliding, stars exploding, dark matter weaving invisible webs. But voids, they're the closest thing to a blank slate, with so little matter that their physics might simplify enough to reveal the holographic code underneath. Imagine trying to read a message scrawled on a foggy window. In a crowded room, the condensation is constantly disturbed, but in an empty one, the words stay clear. Voids could be those quiet, undisturbed spaces where the universe's hidden layer becomes detectable. The real test lies in how gravity behaves in these emptinesses. According to the holographic principle, gravity in our 3D world might actually be a shadow of quantum interactions happening on a distant 2D boundary. If that's true, voids, with their ultra-weak gravitational fields, could expose subtle glitches in Einstein's relativity, tiny deviations where the illusion flickers. Some physicists even speculate that if we map the distribution of voids with extreme precision, their patterns might match mathematical projections from a lower dimensional space, like a cosmic fingerprint revealing the true nature of reality. Of course, not everyone's convinced. Critics argue that the holographic principle, while elegant, remains untested, a beautiful idea without concrete proof. But that's the thrill of voids. They're more than empty space. They're the universe's quietest laboratories, where the most exotic theories might finally meet evidence. If the holographic principle holds up, it wouldn't just revolutionize physics. It'd rewrite our very understanding of existence. Suddenly, those empty voids could be the most revealing places in the cosmos, showing us that reality isn't just what we see, but something far stranger. So the next time you gaze into the void, remember, you might not be looking at nothing. You might be staring at the edge of the universe's projection, where the deepest secrets are written in the language of absence itself. 33rd mystery, void's ultimate fate, the universe's slow unraveling picture, a universe growing quieter every second. Not with a bang, but with a whisper, a gradual fading as galaxies drift apart, their lights dimming into the endless dark. This isn't fiction, it's the fate our cosmos may be hurtling toward, driven by the relentless expansion of space itself. And cosmic voids, they're the architects of this eerie future, silently carving the universe into lonely, isolated islands adrift in an ever-growing sea of nothingness. Right now, voids make up most of the universe's volume, vast bubbles of near emptiness stretching between galaxy clusters. But as dark energy keeps pushing space apart, these voids won't just stay the same, they'll swallow more of the cosmos. Galaxies on the edges of these expanding deserts will find themselves pulled into the void's gravitational drought, cut off from their neighbors as the space between them stretches beyond reach. Over billions of years, the cosmic web, the intricate network of galaxies and filaments we see today, could fray into disconnected specks, each trapped in its own pocket of darkness. This isn't just about distance. As the voids grow, the universe itself cools. Stars burn out, new ones stop forming, and the interstellar gas needed to fuel them gets diluted into near nothingness. Eventually, even the closest galaxies would be so far apart that their light could never reach one another. civilizations born in that distant era would peer into their skies and see almost nothing, no Milky Way, no Andromeda, just an empty black expanse with no clue that trillions of stars once shared their cosmos. But here's the twist: voids might not just be passive players in this grand fade-out. Some theories suggest their accelerating expansion could change the rules entirely. If dark energy's push grows stronger over time, voids might one day rip apart the very galaxies at their edges, shredding them into darkness long before they naturally die. It's a phenomenon called cosmic tearing, where the universe doesn't just cool, it disintegrates. Yet there's a strange beauty in this bleak vision. Voids, often seen as the universe's empty backdrops, could actually be the force that shapes its final act. They're not just spaces between things, they're the canvas on which the cosmos writes its ending. And that raises a haunting question: is the universe destined to become one vast void itself? The answer lies in the delicate balance between gravity, dark energy, and the unseen fabric of space-time. For now, voids are growing, but whether they'll eventually dissolve all structure or just isolate it remains one of cosmology's greatest unresolved puzzles. One thing's certain: the quieter the universe gets, the louder these empty spaces speak, and their message might just be the most profound of all, an echo of how everything ends. 34th mystery: void's human connection, the cosmic mirror that changes everything. It's easy to stare into the abyss of cosmic voids and feel small, insignificant even. But here's the paradox: these vast emptinesses don't just humble us, they connect us to the universe in ways nothing else can. Forget the dazzling nebulas or colliding galaxies for a moment. The real revelation lies in the voids, the silent spaces between everything, because they hold up a mirror to humanity's place in the cosmos, and the reflection is astonishing. For centuries, we clung to the illusion that we were at the center of it all. Then came the cosmic voids, the ultimate reality check. Our Milky Way isn't floating in some privileged spot, it's tucked away in an ordinary galactic cluster, one speck among countless others, drifting along the edge of an unfathomable emptiness. That realization isn't just science, it's a philosophical earthquake. These voids strip away our cosmic arrogance, whispering a truth both terrifying and liberating. We are part of the universe, not its protagonist. Yet this humility isn't discouraging, it's electrifying. Every void we study is a monument to the unknown, a challenge carved into the fabric of space itself. Think about it: we've mapped oceans, scaled mountains, and even touched the void of space near our planet. But cosmic voids, their frontiers so immense, we're only beginning to decode their language. And that's the thrill. Every unanswered question: why dark energy dominates here, how voids sculpt galaxies, what flickers in their darkness, is an invitation. An invitation to explore, to rethink, to push further than we thought possible. Consider this, too: voids are the universe's great equalizers. In a galaxy cluster, chaos reigns. Stars are born and die in violence, black holes collide, magnetic fields twist into knots. But in the void, the rules simplify, the noise fades. It's here, in the quiet, that we might finally spot the subtle signatures of reality's deepest laws, clues to dark matter, quantum gravity, even other dimensions. The emptiest places could become our clearest windows into how everything works. And that's why voids matter, not despite their emptiness, but because of it. They remind us that the universe isn't just about what glows in the night sky. It's about the spaces between, the questions we haven't asked yet, and the humbling, exhilarating truth that there's always more to discover. So the next time you look up, remember, the darkness isn't empty, it's full of possibilities, and in that boundless unknown, we're just beginning to find our way. A final thought: the paradox of emptiness. Cosmic voids have a way of turning our assumptions upside down. What seems like nothingness is actually a treasure trove of unanswered questions. each one a key to unlocking the universe's grandest puzzles. These vast expanses aren't just empty, they're alive with possibility, shaping galaxies, testing physics, and even hinting at realities beyond our own. Think about it this way: if the cosmos were a symphony, voids wouldn't be the silence between the notes. They'd be the deep, resonant bass that holds the whole composition together. Without them, galaxies wouldn't cluster, dark energy wouldn't accelerate expansion, and the cosmic web itself would unravel. They're not just passive gaps, they're active players in the story of everything. And here's the most thrilling part: we're only scratching the surface. Every new telescope, every advanced simulation peels back another layer of the void's mysteries. Will we find proof of parallel universes, detect ghostly particles rewriting the laws of physics, stumble upon a cosmic anomaly that turns science on its head? The answers are out there, hidden in the quietest corners of space, so the next time you gaze up at the night sky, remember, the darkness isn't empty. It's full of questions, of discoveries waiting to happen, of stories we've only begun to tell. And who knows, the biggest revelation might not come from the brightest star, but from the deepest void. What do you think lies in these cosmic deserts? Drop your theories in the comments. We're all explorers here. And if you're hungry for more mind-stretching journeys through the cosmos, hit subscribe and join us as we keep unraveling the universe's greatest enigmas, one mystery at a time. The void isn't the end of the story, it's just the beginning.